two metallic spheres S1 and S2 are made of same material and have got identical surface finish. The mass of S1 is thrice that of S2. Both spheres are heated to same high temperature and placed in the same room having lower temperature but are thermally insulated from each other. The ratio of initial rate of cooling of S1 to that of S2 is. So we have to find out the ratio of the rate of the cooling. So in this case we are going to use the equation that is called as the Stefan-Boltzmann law of radiation for cooling. And based on that equation we can easily find out a solve for the required ratio. Okay. So we start from there that the mass of the sphere S1 is thrice that of S2. So we say that the mass of S2 is suppose given as m. Mass of S2, let us suppose that is given as ms2 and we have taken it as m. So therefore the mass of S1 which we take as ms1 will be equal to 3 times m. Now we write the equation based on which we are going to solve the question, and that equation is Stefan-Boltzmann law of radiating cooling. So this is Stefan-Boltzmann law of radiating cooling. And this relationship tells us the rate at which the energy leaves an object due to radiation. You can say the rate at which energy leaves an object due to radiation. And the equation is given as delta Q upon delta T. This gives us the rate of heat loss and will be equal to epsilon sigma A multiplied by T raised to power 4 minus T raised to power T naught raised to power 4. And here the epsilon is given as emissivity of the surface, A is our surface area of the object, sigma is the Stefan constant, T is the temperature of the object, and T naught is the ambient temperature. Now we are going to find out the value of delta theta, which is nothing but heat energy lost by the sphere. So delta Q, sorry, not theta, delta Q is our heat energy lost by sphere. It should be lost by the object, but here in case the object is the sphere, so we write heat energy lost by sphere. And this delta Q is given as m multiplied by c and multiplied by delta T, where m is the mass of the object, here it is sphere, m is mass of sphere, c is our specific heat, and delta T is change in temperature. Change in temperature. Therefore, we substitute value of, you can say, delta Q in the Stephen equation. Let us call this as equation number 1. So we can say from equation 1 we get delta T upon time is equal to epsilon sigma A T raised to power 4 minus T naught raised to power 4 and whole divided by m multiplied by c. So in this case, all the things can be treated as constant except the value of A and the mass m. So we can say from here that our rate of change is proportional to A upon m. Now let us find out what will be the area of the sphere and what will be the mass of the sphere. Then we are going to substitute those values in this equation. And A is our surface area. So we can say surface area and mass relationship. Surface area and mass relation. So for sphere, our volume V will be directly proportional to R cube. Mass we know is density multiplied by volume. So therefore, the mass is also directly proportional to radius cube. Now is our surface area. It is A, and that will be equal to directly proportional to R square. So using the equation for surface area as well as the equation for the mass, we can write that our A is directly proportional to R square and is directly proportional to m 2 by 3. So let us substitute it in this equation number 2. So we can say from equation 2 we get delta T upon T is proportional to m raised to power 2 by 3 and divided by mass m, and which comes as m raised to power minus 1 by 3, or we can say m 1 upon m raised to power 1 by 3. Therefore, we have to find out the cooling rate for both the spheres. So let me write it separately. Delta T upon T is proportional to 1 upon m raised to power 1 by 3. And this relationship will be true for both sphere 1, that is our S1, as well as sphere 2, that is our S2. Sphere 2, that is our S2. So let's modify this equation as per our spheres. So we can write that rate of cooling we are supposed to find, I think a ratio we have to find out, no? Let me check. Yeah, ratio. Okay, so let me modify this statement. Rate of cooling ratio. So we get this as delta T upon T, rate of for sphere 1 divided by cooling rate for sphere 2 will be equal to mass for sphere 2 and mass for sphere 1 and whole raised to power 1 by 3. We substitute value, we'll know mass 2 is our m and mass for sphere S1 is our 3m and whole raised to power 1 by 3. M cancels with m, so therefore we get the ratio is equal to 1 upon 1 by 3 and whole raised to power 1 by 3. So the option correct one is our option number is, I think B and D looks kind of similar. Sorry, not similar, my mistake. There is square root. So option number D is the correct option. You can say option D is correct. Option D is correct. So this completes the question. Thank you.